I will talk about surface transverse wave resonators, and my courses are Vensi Yanchev from Uppsala or Göteborg universities, and Michael Yan and Bob Xiao from here, from Taipei. Doesn't work. Here. Okay. Okay. After discussion of motivation, I will present some experimental data, then some theoretical considerations about this data, some simulation, 2D simulation and 3D simulations, and compare experiment and theory. STW resonators have excellent parameters, that is very good approach for gigahertz frequencies. For 2 gigahertz, here is a measured example which we designed some time ago. It is produced already many years, and the device works at about 2 gigahertz and has about 8,000 Q factor, and some devices have 10,000. But what we have observed is some ripples in some cases, and these ripples, this is 2-port device, but of course for one, and you have a kind of 2 resonances here, but for one resonance you also have these ripples, and they are very damaging, especially for oscillator design, because of monotonic change of phases necessary. So we tried to understand where it comes from, and we have developed a set of test devices which included different aperture four apertures from 10 lambda to 80 lambda, and also different kind of dummy fingers. There was devices with no dummy fingers, with long but regular dummy, regular in terms that they have the same metallization, and we had also wider dummy fingers. So we had a matrix of 12 resonators. We measured a lot of them, and the first conclusion which you can draw from these pictures is that aperture is very dramatic parameter. The larger aperture we have, the better Q factor we obtain. Probably we could go a little even further, but of course at some moment resistivity will work, so you can, there is optimum there. We had 2% metallization thickness and 4% metallization thickness. And as you see, we had quite good devices with Q factor up to 10, close to 10,000. I cannot, of course, present all curves here, but just a few examples. What we have measured, that is narrow aperture device, and then if we have no dummy fingers, then we have mediocre, very mediocre curve with a low Q factor, and the presence of dummy fingers, especially wider dummy fingers, radically improves Q factor. For larger aperture, it is about the same, and also in this left side, we have some oscillations in real part of admittance, so we have some absorption somewhere here, which depends also on presence or absence of dummy fingers. And about the same situation is for 4% metallization, but we also see that if we have dummy fingers, we can get splitted resonance, which is very unpleasant for resonator, and for wide aperture it also depends on this splitting depends on presence of dummy fingers. So how can we understand all that? other people, this is pictures, two pictures, this and this from Marcus Meyer paper from EPCAS. They also have seen these peaks. So they are attributed to a kind of transverse mode, but they are on left side from resonance. Normally transverse modes are on somewhere here on right side, and here we have them on left side. And the Marcus theory was that it is due to special concave shape of slowness curve. Really, in this material, this is 36 quartz and perpendicular to X propagation direction. We have this concave shape of slowness curve in plane of substrate. And that basically means that if we have propagation with some angle, we have a reduced velocity. Velocity strongly reduces with some angle. And because of that, we have kind of everything in opposite order. For lower frequency, we have evanescent modes, and for higher frequency, we have propagation modes, opposite to what we normally would have for isotropic or circular or kind of slowness curve. And that can explain that this transverse mode appear on left side from the main resonance. But the problem is that because of Bragg reflection, the resonance has even smaller velocity than bulk waves or waves in busbar. That is exactly my case. I will not stop on Marcus' case because he had 6% and we have 2%. So for 2%, this blue curve is a kind of bulk skimming wave, and the reddish curve is busbar, solid busbar curve. But STW in grating will be, because of Bragg effect, because of left side of Bragg's band, it will be here. So it is even slower. So on slowness curve, we are on right side. And you see that you have, at the same slowness, you have intersection with both of these curves, which basically means that if you have a resonance at the same velocity, you have bulk waves in busbar and even skimming bulk waves. The wave and structure is coupled with busbars and even with bulk skimming waves. So it basically means that you, at least for this small thickness of aluminum, you never have waveguiding, ideal waveguiding. You always have some radiation into busbars. There is another way to present that, but this picture looks too complicated. It has two different sides. This side are just normal dispersion curves, and to be short, I will say that from this blue curve is waves propagating in a periodic structure, and red is waves in just bulk waves, bulk surface skimming bulk waves. So this distance is stop band, and our resonance is normally here. But if you have a periodic structure and you take inclined propagation, what will happen with this stop band? This stop band will move down. It will move down on frequency. So this right side is a kind of Bragg situation all time, but for inclined propagation. And the result is the same. If you have resonance here, for the same frequency, it is coupled with waves in busbar, and it is coupled with bulk waves. So whatever you do, you have losses, and that explains why you need wide aperture. If aperture is small, you have losses in busbar. If aperture is wide, you have the same losses, but you just have more energy. So your Q factor is increasing because of that, because losses are proportional to line and energy is proportional to area. But we found how to fight with this effect. You can use busbars with wider metallization. And what happens again, that in this case velocity is going down, so your resonance, which is here, will be not coupled with any propagating wave, at least at some frequency range, propagating waves in dummy fingers. So dummy fingers will isolate your acoustic channel from busbar, and you are close to ideal resonator. And that explains why dummy fingers help. They just make real propagation without radiation energy into busbars. We have had simulation with COMSOL, and here it is one of the examples, and it really confirms that what we say, that we have propagation into busbar area, and we have radiation in bulk in this kind of resonators. And now we have also very good 2D software which allows numerically calculate practically whatever device. This device had almost 700 electrodes, and we still can simulate finite resonator with 700 electrodes. And what you see here, that simulation and measurement have absolutely all the same peak, which basically means that all these peaks are not transverse mode. It is just finite structure. It is transparency of resonators and interference of waves from transducer. So some peaks which you can get on the left side are just this kind of finite peaks, and you can fight with them with using known methods. I will omit this picture because I have no time. Finally, it is interesting to try to model this splitted kind of resonances, where they come from. And you see here this peak. This one corresponds to this picture, and it is basically resonance, but because we have a very close bulk propagation in busbars, we have a kind of mode which has both, which has what we expected and which has a kind of propagation in busbars. But we have even stronger mode, which is a kind of opposite, when the limited wave, which is decaying in both sides, is propagating basically in busbar area, near busbar, but simultaneously, because frequencies are so close, simultaneously something excited here. So basically we have really two transverse modes here. If we go to small oscillations where we see more far from resonance, they look like transverse mode, but they are not transverse mode because we have no waveguiding there. It is simply transducer generates a plane wave and generates waves propagating with some angles, and they give this interference picture. But don't forget that it is dB scales, so it is 40 dB lower this small oscillations. That is basically what I wanted. What I wanted to show you. I have two strong conclusions. First strong conclusion is that STW resonator always radiates something in busbars if you do nothing special. And then you need the aperture, big aperture, to have a good Q factor. And second strong conclusion is that we found how to localize energy inside the structure if you use this wider busbar. And everything looks opposite here again, because you need wider busbar to make waves localized in the middle, where busbars is narrow. So in normal case, without this concave structure, you would have opposite. Thank you for attention.